programme, we're going to talk about far infrared astronomy. And some people won't know what that means. What is far infrared? Well, here we have three experts, Chris North and John Risher, and they cover almost the whole field of astronomy, which I most certainly do not. So here they are. Good evening.
Good evening, Patrick. I'm delighted to be talking about the infrared because we can use it to look at the really cool stuff in the universe.
Quite.
By which I mean cold, of course. That seems a little counterintuitive, but makes some sense. We're used to looking at the universe with our eyes. We're used to getting visible light through telescopes and cameras, but we're biased towards the bits of the universe that shine, whether they're stars or even light bulbs that shine and give out optical light. If you look around this room, most of the stuff we can see, yourself, the table, even our guests here, we see them because they're reflecting that light. But they're also shining. They're shining in infrared. And one way to think about that is to look at a glowing coal. Imagine a red-hot coal. It'd be giving off faint light, but if you hold your hands out to the coal, you can feel heat. And that heat is because of the infrared radiation, just a longer wavelength form of the light. In fact, we could demonstrate some of this by playing around with an infrared camera that you've got, Chris.
Yes, so here we have a camera that's showing, at the moment, Patrick in the infrared. So what we're seeing here is light that Patrick is giving off. We can see that the yellow stuff is warmer, the yellow and white is warmer. And Patrick, you have a cold nose.
Yeah, and a cold monocle.
Yes.
But that's
I have
well.
also a very black cat.
Yes.
So the picture of Ptolemy the cat in the infrared. And we can scan this around the room, and you can see that the things that are normally hidden are now seen. The camera crew and the lights are glowing in the infrared. And here we have John as well.
Very warm.
Yeah, very warm. Not quite as cold a nose as Patrick.
And you can see that this is a different view of the world from the visible universe, because we've got two mugs here, Patrick, that look pretty much identical, filled with water. And they look the same in the optical, but in the infrared, Chris, what do you see?
Well, the one on the left is certainly black, so that's very cold, and the one on the right is white hot.
Yeah, so this is actually filled with hot water from the kettle, this is iced water.
And that's something you can't tell using just the optical light. It's something you need the infrared to be able to tell, or you have to be able to pick them up. And one of the problems with astronomy, of course, is it's rather difficult to go and pick things up.
It is indeed.
And so, John, what do we see when we point an infrared or even a longer wavelength telescope at the sky?
Well, the key difference, as you've said, from the optical, where we see stars, the hot things in the universe, we see the bits of the universe which are cold. So between the stars, which is largely empty space, there are clouds of gas and dust. Particularly, they come in various forms, but the ones that are particularly interesting are called molecular clouds. And in these clouds, there's a collection of molecules and dust particles, and they're only a few, maybe 10 degrees above absolute zero in temperature.
And it's about minus 273 centigrade.
That's right. So the clouds that we can see, these molecular clouds, typically are at minus 263 degrees Celsius, or 10 degrees above this absolute zero. And then the little molecules in the clouds, different molecular species, and they rotate at different rates and make jumps between these different rotational states. And when they do that, they emit little packets of light at particular distinct frequencies.
And an astronomical infrared telescope doesn't look at the least like an ordinary telescope.
Tell us about the James Clerk Maxwell telescope, JCMT.
Yes, the JCMT is a telescope that's been operating now on a remote mountaintop in Hawaii for over 20 years now. It's a reflecting dish. It's a large reflecting telescope, 15 metres diameter. But at the focus, we put these special far infrared cameras that detect the far infrared radiation, a bit like the one that we've just been demonstrated by Chris North here.
The really difficult thing is you have to make the detector quite cold itself, because otherwise all you see is the camera.
That's right. So the newest camera that's operating now on the James Clerk Maxwell telescope is called Scuba 2. It's a very new project, and inside there's a very large far infrared camera that's cooled to only 1/10 of a degree above absolute zero.
We should explain why the pictures look so terrible. Because for people who are used to looking at Hubble pictures, that we're used to looking at the visible, we're into the science of blobology here, right? Well, why is it so hard to get a decent image at these wavelengths?
In the far infrared, the wavelengths are much much longer than in the optical. So although we have a 15-meter telescope, the resolution of the images we get isn't very good. In fact, the resolution of the James Clerk Maxwell telescope is very similar to that of the unaided human eye, which is quite good, but in terms of running our daily lives. But in terms of the detail we need to study astronomy, it's not good enough for many of the observations we want to make.
Well, nonetheless, what can we see? For example, if we point it at M17.
What we know is that in these large molecular clouds, new generations of stars are forming as we speak. And so by mapping the large structures in these molecular clouds, we can find where the new stars are forming.
To go and take a very close look, we're going to need a different telescope. And luckily, there's one being built. It's probably the most ambitious international collaboration in astronomical history. And the telescope's called ALMA. It's down in Chile. And a few years ago, I went and had a look at the site, and there wasn't much there then. But John, things are pretty different now.
So ALMA was designed to work in the same part of the spectrum, the very far infrared, as we observe with Scuba 2. But it was to address the fundamental problem with Scuba 2, which is although it's great for seeing the big things in the universe and surveying where all the stars are forming, what we can't do is zoom in and look in very great detail.
ALMA can do that.
Yes. So obviously the JCMT is a 15-meter dish, and we worked out that to look at these objects in detail, we needed a dish which was 15 kilometres in size. Now clearly that's impossible to build.
It's a bit difficult to steer.
Yes, and way beyond our budget. But we utilised the technique of radio interferometry, where we recognise that in fact you don't need to build all of a dish, all of a mirror, in fact, to make a good image. You can build parts of the mirror in different places. So in this case, we've got a 15-kilometre size plateau up high in the Chilean Andes, and we have 66 separate radio antennas which are spread around this site. And we take the signals from each of those antennas and combine them essentially in an electronic focus, if you like. And at that electronic focus, we can make images, and it's as if our telescope had a diameter of 15 kilometres. So that means that images are 1,000 times more detailed than the JCMT.
And so for the first time, we actually now have, getting with ALMA, images that can compete in resolution terms with optical images, which is something that I think infrared astronomers have always been very jealous of optical astronomers. So we've talked about the technology behind these and how complex it is, and there's a lot of work going in around the world to build these, and some of that is taking place in the UK, and I went to the Rutherford Appleton Laboratory in Oxfordshire to find out more. The Rutherford Appleton Laboratory has a worldwide reputation for building fabulous astronomical instruments, which end up on telescopes all over the world. High in the Chilean desert, the ALMA telescopes are looking at the cold part of the sky, and to do that, they need to be kept as cool as can be. Telescope dishes are big and impressive, but they're just light buckets. It's the scientific instruments, the unsung heroes at the back of the telescopes, which are doing all the hard work. It's their job to receive the light collected by the dish and turn it into the amazing scientific results and images which will wow us. At the Rutherford Appleton Laboratory, Professor Brian Ellison is helping build the space-age refrigerators which will help keep the instruments cool. It's a chance for me to immerse myself totally in some superconducting tunnel junctions and local oscillators. Just my kind of fun. So Brian, we've got in front of us the heart of one of the receivers of ALMA. Tell us what we're seeing here.
Okay, this is one of the superconducting tunnel junction receivers of ALMA that detects the energy from the telescope focus. What happens is that the signal from the telescope comes down through, bounces off various mirrors here and is brought to another focus at the detector here. This device works at 4 degrees Kelvin, that's 4 degrees above absolute zero, and picks up the energy, and that propagates down these cables here at a frequency of about 4 gigahertz, out through various components. It's amplified down through the rest of the structure and out to the outside world.
So this is one of the receivers, and there are quite a few of them in each cryostat. So
yes.
if you look at the back of here, we've got quite a range of them.
Yes. Here we have the rear end of the ALMA receiver system. What you're seeing here is an array of the different local oscillator assemblies that provide the receiver reference signals.
So we've got light coming in from the sky, compared with this reference source that comes in from the back, they're mixed at that detector we just saw, and the resulting signal is fed out the back.
The results in fed out the back. Basically, it's a radio receiver, but it's working on a much higher frequency than the average radio set.
So far, 16 of these space-age receivers have been fitted to telescopes on the Chajnantor Plateau, with 50 more to follow over the coming year. The ALMA telescope has already started giving us an amazing view of the Antennae galaxies. In visible light, we see two galaxies which are in the process of colliding, each containing billions of stars. With ALMA's ultra-cold eyes, we see the gas and dust between the stars, providing our first detailed view of the galactic crumple zone in which new stars are forming. ALMA is sure to amaze us even more over the years and decades to come, proving that it's cool to be infrared.
We've been talking about telescopes on the ground. What about telescopes in space? Of course, so far, the most ambitious infrared telescope in space is Herschel.
Herschel's now been up there for 3 years. It's the best far-infrared telescope we've got up in space. It's looking at wavelengths that are slightly warmer stuff than Scuba 2 and ALMA are. But one of the key things is that these are wavelengths that are completely impossible to observe from the ground because the atmosphere is essentially completely opaque over most of the range.
Yes.
So take the Pillars of Creation from Hubble. It's one of the most iconic
Yes.
images.
These dust clouds against a bright
Oh,
background.
they're amazing things, yes.
The optical light we're seeing there is gas on the edges of these 3 fingers that are being energized or ionized by starlight from some nearby young stars. But if you look in the infrared, you're not seeing the gas, you're seeing the dust itself glowing. And what you can then tell from the temperature of the dust, you can see how many stars are in there that are heating the dust up. And then if you see some very cold clumps, these are the stars that are starting to form. I think one of the interesting things that always surprises me about star formation is that the coldest things we know of in the universe are about to become some of the hottest things we know in the universe. So we can see much more about where stars are forming and the environments that stars are forming in, but it can also look at enormous areas. You can get images of 6,000 galaxies in, and so the images are typically a few times the width of the moon across. But even if you take something that's the size of your little finger held at arm's length, there's still 1,000 odd galaxies in there, and these are at times when the universe was only a few billion years old, typically.
One of the things that Herschel can uniquely do is allow us to study water in the universe. Now, even in Chile, on that very dry site, there's enough water in the Earth's atmosphere to block out the signals from water molecules emitting in these clouds.
It's not impressive to discover water in the Earth's atmosphere, I'm afraid.
No, that's right, but Herschel, being above the atmosphere with its very specialised receiver, can tune to some of the frequencies when the water molecules change their rotational state. We can get these spectra of water in star-forming regions.
The results are surprising, right?
I think to a large extent we've detected much less water than we expected based on our model. So there's still a mystery there as to really understand the whole process by which water forms. We know it has to form in quite large abundances, but the signals so far have been somewhat weaker than we were expecting.
We've been talking about Herschel as one of the best infrared space telescopes. There's another one up there which is also very impressive. It's called the WISE satellite. That's been looking at slightly different wavelengths, and I went to speak to one of the lead scientists involved, Amy Mainzer.
NASA's big infrared mission, WISE, was designed to map the cosmos, and also to discover new objects that no other telescope could see. It could only work for a year, but in that short time it collected an amazing amount of information. Whilst in Nantes, France, I caught up with one of the team, Amy Mainzer.
We collected millions of pictures.
Sure.
We took a picture every 11 seconds for a year with a 4-megapixel camera, so you can imagine, that builds up a lot of data very quickly.
Yeah.
So imagine trying to go through that slideshow. I mean, it would take a while.
Hiding in the dark and amidst all that data was a strange object, and the WISE team found it. A new type of star.
Well, one of the most fun things that we've discovered so far with WISE is something called a brown dwarf, and it's a new class of brown dwarf that is actually room temperature. This is a star that can't even boil water. At its surface, it's about room temperature. It's very cool, and it's basically kind of like a more massive version of Jupiter, if you will. These are things that are sort of halfway between the stars and the planets, and they're probably more like a planet in some ways than they are like a star.
Okay, and the processes going on in their core are not quite the same as what goes on in a
Right.
in a star, in
Right.
a star like the sun. Rather.
Yeah, some people like to call brown dwarfs failed stars. They're stars that are not very good at being stars because they can't fuse hydrogen into helium. What makes our sun glow is, it's so, gravity is so powerful at the center that it can take two hydrogen atoms and jam them together to make a helium, and that releases a lot of energy. But these brown dwarfs, they just don't have the mass. They can't do it. They cannot push the hydrogen atoms together to
The
make
temperature
helium.
and density just isn't
It's
high
just
enough.
not
in the
enough.
center.
That's right.
Okay.
So they're kind of like, wimpier versions of our sun, lots wimpier. And so what happens is when they form, as they collapse and out of a cloud of gas and dust, they get hot in the middle.
Right.
But unlike our sun, which then starts to shine of its own accord through fusion, these guys just cool off.
You can see these with WISE,
Yeah.
and you'll find them surprisingly close. As
Yeah,
well.
that's right. That's right. So one of the things we were really interested in doing is seeing, are there stars that are as close as the ones that we know to be closest? And maybe there are stars that are even closer. So the search is on. We're hunting through these images right now to cull out things that look like they might be these very, very cold, very nearby brown dwarf stars.
WISE has also been searching the cold, dark depths of our own solar system, hunting for asteroids. In particular, ones that could threaten the Earth.
We were actually able to observe more than 157,000 asteroids in our solar system. That's about a quarter of the known population. Most of these are in the main belt between Mars and Jupiter. But we were also able to independently discover about 33,000 asteroids so far.
Okay.
And that number keeps changing as more and more observations get connected to other people's.
Okay, and you're analysing your data again and again and again. I
Yeah,
assume.
that's right. So that's one of the fun things about studying asteroids is it's just constantly changing. It's a really fast-paced field. It's a lot of fun. Keeps us busy.
Most of the asteroids stay in the main belt,
Right.
but some of them stray. So
As of today, we know of about 8,000 or so near-Earth objects that have been discovered by observers all over the world, going back even hundreds of years. But today what we have with WISE is a different kind of a sample. It's a unique sample in the sense that because we were able to observe these near-Earth objects with infrared light, we're able to get really good measurements of sizes of asteroids. Most surveys have looked with visible light, and that means what they're sensitive to is sunlight bouncing off the surface of the asteroid, so they depend a lot on how reflective the surface is.
right.
That makes it hard to tell the difference between something that's small but very bright or shiny and something that's large but dark.
It's because there's a lot of these things that people think, maybe not the asteroids, but comets and something we thought were made of ice
Right.
and therefore shiny.
Yes.
And that was
There's a huge amount of diversity in all of the asteroids and the comets. And in fact, if you just look at the average rocks that you see around you on Earth, well, there's just as much diversity among the asteroids. And if we have both infrared and visible light, now not only can we measure the sizes very well, but we can even measure how much sunlight is reflected off the surface.
So WISE had to be cooled to work, and
Right.
that meant that eventually that coolant, the refrigerant, ran out.
That's right.
And so that part of its mission ended.
Yeah, the mission is now in honorable retirement. It's
Right.
completed all of its mission goals and then some. Actually, we completed an extended mission, and now we're done. The survey part is done, and now we're processing the data.
Big missions like WISE leave long legacies, and it will take many decades for astronomers to sift through the millions of images it has taken. Who knows what further discoveries will be made?
WISE has finished its mission now, but it was great to hear about it, and the data will be useful for years to come. But it does raise the question, John, how do you see these different surveys on different scales, at different wavelengths? How do they come together?
Yeah, well, we're very lucky to have Herschel up and flying and operating and ALMA just coming online simultaneously, because in fact it's by putting the data together from those two great telescopes that we learn most. We build up what's called the spectrum, or the spectral energy distribution of the object. And so by building physical models in our computer of these objects and comparing them with the data, we can work out exactly how stars form.
Let's say we gather here again in, let's say 5 years' time. ALMA will be up and running. What will we know? What do you think the big discoveries will have been?
We already know, of course, that there are lots and lots of exosolar planets out there, and so we know we have to have a way of forming those. So my hope, I suppose, for ALMA is that over the next 5-10 years of observing, we make good enough images of protoplanetary disks to really understand the details of how exactly stars form, where they form, when they form, and how they maybe migrate through the disk to occupy their current locations.
Well, it's all fascinating stuff. John, Chris, thank you very much. So let's go now into my garden, where we find Pete and Paul also looking at the infrared sky.
Well, I think any chance of seeing stars tonight, Pete, is entirely wishful thinking. Look at all the cloud.
It's a bit of a problem, isn't it? I mean, there's a thick blanket of cloud up there.
It's depressing.
And it looks pretty uniform when we look at it visually. But I have a very special camera here, which is an infrared camera. In fact,
yes.
Well, it's sensitive to the mid-infrared range. And when you point that one up to the sky, it can see clouds as well.
Right.
So it can't see
Well, that's
through
brilliant.
the
It's
clouds.
a useful device.
But unlike out when we're looking at the sky visually, we're seeing it just as a uniform blanket of cloud. We can actually pick out structure in it when we're looking through this camera. So it's good for picking out holes in the cloud.
I gather it's on me at the moment, so it can pick out my nice velvet jacket that I have for Christmas.
It can. It's basically what it's doing. It's picking out all the different temperatures of your body as well. So
the cold hands.
it actually looks like you've got sunglasses on.
Oh, they reflect it quite.
Yeah, but the problem with infrared, if you're trying to look at stuff in the sky which is emitting infrared, is the Earth's atmosphere, the water
course,
vapour
yes.
in the Earth's atmosphere. And that means that for amateur astronomy, we have a bit of a problem, because unless we actually get rid of the atmosphere above us, we can't see anything in those ranges. But there are bits and pieces we can do, mainly in the area of planetary imaging.
And just on that subject of planetary imaging and infrared, that we have a little story, and I don't know if you're familiar with a phenomenon called the Ashen Light.
Oh, yes.
It was seen by Giovanni Riccioli January the 9th, 1643.
Right, okay.
And he noticed that there was this faint light on the dark side, the night side of Venus, and it kind of looks a little bit like Earthshine.
That's right, that's the effect you get when you get a really thin crescent moon in the evening twilight or in the morning twilight.
That's right.
And that's caused by reflected light from the Earth, but of course that can't possibly be the case with Venus.
Really nothing to do with it on Venus. And it's a very, very vague thing. Sometimes it covers the whole of the dark side of Venus, and other times just portions of it. And it's a sort of greenish glow, very, very subtle. And I know you are quite sceptical. I can tell you've got that look in your face. I don't believe a word of it. It's just visual people seeing things. It is. I think there is a genuine phenomena there.
There are a hell of a lot of reports about the Ashen Light. The problem with it is that when you have a crescent Venus, it looks like it really wants to complete the circle. Now, I'm very open-minded. I'm quite happy if somebody comes along and says, look, there's the Ashen Light, there it is. I'll be quite happy to accept that, obviously. But I have tried and tried using near-infrared filters, because that's where it's supposed to be at its brightest. Pushing the crescent of Venus off the side of the frame and really upping the sensitivity of the camera, and I've picked nothing up at all.
Sure, so I tell you what, I will bet with you within the next decade that it will be shown to be a genuine phenomena.
Decade's an awfully long time,
Yeah, you can
but
do
okay,
it.
let's go for it.
You've witnessed this.
What do I win?
Yeah, respect. Now, but Venus isn't the only thing we can do with infrared. You've used it with Mars and Jupiter, haven't you?
Yeah, basically you use a near-infrared filter. When you look through one of these filters, it actually has the effect, because you're using a slightly longer wavelength than normal visual part of the spectrum, the seeing is actually a bit steadier. So that helps us if we're trying to take high-resolution images of Mars, particularly Mars, Jupiter, Saturn and the Moon, because it allows us to get a much more steady view of these things. But also, the infrared actually starts to crisp up. It gives a greater contrast in some features, particularly with Mars, because Mars is a very reddish planet.
Of course, yeah. So those albedo features are going to be exaggerated.
They stand out brilliantly, actually.
Right. Coming back to Venus, there is an interesting conjunction in March, isn't there, with Jupiter?
Ah, yes, that's right, because Venus at the moment is sort of moving away from the sun, and Jupiter is gradually marching in towards the
So they're going to have a little
twilight.
encounter.
And they will have an encounter, which is called a conjunction. And that will occur or be at its best in the middle of March. Now that's going to be pretty spectacular, because you've got two really bright planets. Venus is the brightest planet of them all. I think Jupiter, actually, I think Mars can marginally get brighter than Jupiter.
Yeah, but not this time.
But not this time, no. But when they're together, they're going to look like an amazing, really bright double star.
You're going to be out photographing them, aren't you?
Of course.
Well, it'd be lovely to have some of these images in to our Flickr site, wouldn't it? So if anybody does any infrared stuff or captures the Ashen Light, that would be wonderful.
Yeah, it'd be absolutely amazing.
Well, if you want to see all our lovely pictures, go to our BBC Flickr site, which is located at bbc.co.uk/Sky at Night. All these wonderful objects for February and March, Pete. Aren't we lucky?
We are indeed.
Well, in from my garden with the two Chris's. Chris Lintoff, first of all, this picture of the Helix Nebula, and it's infrared, and it's a lovely picture.
It's a wonderful image, Patrick, in the infrared from the Vista telescope down in Chile, and it really shows the interaction between the gas, which is the outer layers of a sun-like star near the end of its life that's been shed, and the star itself, because you can see these dusty rings of different layers. Then you can see these fingers, which are being illuminated by the central star. It's an incredible image and a beautiful object.
Another thing that's on the other sun has survived so far is a sun-grazing comet.
Yeah, so this is a comet that goes by the name Comet Lovejoy, named after Terry Lovejoy, who discovered it at the end of last year. And it went incredibly close to the sun. It went within about 140,000 kilometres of the sun. Incredibly close, incredibly hot. You would expect a comet that goes that close to be broken up and to evaporate. And that's what was expected to happen. This comet went past the sun and then miraculously came out the other side intact. So it must have been much bigger than it was previously thought to have survived the encounter.
And some of the images are just gorgeous. I mean, you can see this glorious comet. And why on earth couldn't this have happened in the north of the sky, Patrick? This is...
Why did it come closer to the Earth?
Yeah, this is just not fair, but a beautiful comet nonetheless. I hadn't realised that all of these sun-grazer comets, most of them are supposed to come from the breakup of a single larger body not that long ago. So we're seeing the dying embers of a past massive comet. Rather wonderful.
Well, now also yet more planets of other stars. Getting a bit tired of these.
Well, these are exciting ones. I mean, I know what you mean, but we just caught, our last programme was on exoplanets, and we just caught the discovery of the first unambiguously Earth-sized and Venus-sized worlds, but it's been topped already, and we have 3 Mars-sized bodies, and they were able to be detected because they're very close to their parent star. And so we're really getting down to rocky planets now, and they too, I think, will turn out to be common. In fact, we have a survey that used a technique called microlensing, looking for the bending of light from distant stars. A team looking at this microlensing data predicted this week that there are probably 100 billion planets, at least, in our galaxy. So you're going to be bored of them for a while yet, Patrick.
Many of those must contain life. I wonder what it's like.
Yes, well, let's hope they're watching. But let's come back to your province. Let's leave life alone for this month and talk about the moon, because there's a new NASA mission.
Ah, yes, indeed. An interesting one, too.
Yeah, so this is a mission called Grail.
0 and liftoff of the Delta II with Grail. Journey to the center of the moon.
And it's 2 spacecraft that are going to fly in immense precision around the moon. And as they do so, as they pass over massive regions, they will dip, and as they pass over less dense regions, they will rise, just by the differences of the moon's gravity. By doing that, they plan to map the interior of the whole moon, and we'll get a sense of how the moon formed.
And it's something that's going to tell us about why the near side of the moon is so different from the far side of the moon. We think that's because of the way the moon forms, and hopefully the Grail satellites, which have now been renamed by some students in America who won a competition. They're not called Grail AM and Grail B, they're now called Ebb and Flow, which is very...
Oh dear. And with that, I think we'll say good night.
Yes.
And I'll be back next week, this time talking about amateur astronomers and the work they do in astronomy, which, believe me, is very considerable. So for now, for all of us, good night.
Friday night on BBC HD means Baka, Cry from the Rainforest, a return to the Pygmy Baka tribe for filmmaker Phil Aglands. And that's at 9 o'clock.